Early computer architectures faced a severe structural bottleneck when moving data. In standard programmed I/O or interrupt-driven I/O, every single piece of information had to be processed directly by the central processing unit. Moving a file wasn't a passive physical copy. The CPU had to actively execute a specific software instruction to fetch a byte from a peripheral, and then execute a second, separate instruction to write that byte into memory. This creates an inefficient physical routing path. Instead of traveling directly from the source to the destination, the data payload bounces into the CPU's internal registers first, and is then pushed back out to the system memory module. During a bulk data transfer, like reading a sector from a hard drive, this constant fetch and execute loop monopolizes the processor. It cannot calculate math, process application code, or perform any other logic tasks while the transfer is occurring. Relying on the processor as a mandatory middleman prevents architectures from scaling I/O bandwidth. Achieving high-speed bulk transfers required an entirely separate hardware pathway. This alternative hardware routing is called direct memory access, or DMA. It permits peripheral devices to write directly to system memory without routing the data through the CPU. In many early microprocessor designs, this direct pathway is governed by a dedicated chip known as the Intel 8237 DMA controller. The 8237 operates in a split-state reality. Most of the time, it acts as a standard slave peripheral, taking instructions from the CPU. But when a transfer triggers, it steps into the role of the master processor, taking physical control of the system buses. We are going to trace the exact chronological lifecycle of a single data transfer. We will look at the slave mode programming, the hardware handshake required to usurp the bus, and finally, the master mode execution. Analyzing the 8237 details the first principles of hardware arbitration and state-machine metamorphosis. Before data can move, the 8237 starts in slave mode. It sits passively on the main system bus, waiting to be configured by the central processor. Looking at the 8237's internal registers, the CPU preloads parameters into the memory address, count, and command registers. To address these, the CPU drives the chip select line low and uses the A0 through A3 address lines to pinpoint the exact target register. The setup sequence begins by disabling the 8237. The CPU issues this command to ensure the chip does not accidentally trigger a transfer while its parameters are actively being loaded. Next, the CPU writes a control byte to the mode register to establish the operation's rules, the direction of the data flow, whether the address should auto-increment, and which channel executes the move. The CPU specifies the target memory location by loading a 16-bit starting address. Because the data bus is only 8 bits wide, the CPU executes two sequential write operations, first sending the low-order byte, followed immediately by the high-order byte. Following the address, the CPU sends a 16-bit value to the word count register, defining the exact size of the data block to be transferred. With the memory location and block size locked in, the CPU clears the mask bits and re-enables the DMA controller. This sequence of software instructions successfully arms the hardware state machine. It is now fully programmed and waits silently for a physical trigger. The catalyst for the transfer occurs when an external device, like a floppy disk drive, is spun up and ready to output data. The peripheral signals its readiness by pulling the DMA request line high, sending a voltage into the armed 8237. The controller reacts instantly, outputting a hold request signal directly to the CPU's hold pin. The processor registers the interruption, but must finish its current machine cycle. Once complete, it enters a tri-state phase, floating its address, data, and control pins into a high-impedance state, severing its connection to the system buses. To conclude the handshake, the processor asserts a hold acknowledge, or HLDA, signal back to the DMA controller. Receiving the hold acknowledge is the exact point of metamorphosis. The 8237 drops its slave identity and officially becomes the master processor of the system. As the newly crowned master, the 8237 must now output a 16-bit address to target the system memory. But the physical chip is constrained. It only possesses 8 dedicated address pins. This schematic shows the solution to the pin deficit: time multiplexing. The 8237 routes the missing high-order address byte through its data bus. To safely route this, the DMA asserts the AEN signal, disabling the CPU's logic and enabling an external 373 latch. The 8237 briefly places the upper 8 bits of the memory address onto its data pins. During that window, it fires the address strobe signal, trapping the transient byte inside the external latch to form the top half of the address bus. At the same moment, the controller outputs the lower byte of the address directly onto its dedicated A0 through A7 pins. By spatial multiplexing its data lines and using an external latch, the 8237 establishes a 16-bit address, proving logical timing can overcome physical pin counts. With a stable 16-bit address locked onto the bus, the physical transfer of the payload begins. The controller sends a DMA acknowledge or DAC signal to the peripheral, granting it permission to place its data onto the active bus. The 8237 asserts control signals, pulling I/O read and memory write active. This moves data directly from peripheral to RAM at maximum speed. During transfer, internal logic tracks progress. The memory address increments to the next byte, while the word count decrements by 1. This process repeats autonomously until the word count register hits exactly 0. When the count runs out, the DMA fires an end of process, or EOP, signal, notifying the peripheral that the specified block transfer is finished. The system tears down the connection. The 8237 drops the hold request signal. The CPU reconnects its pins to the bus, and the controller reverts to passive slave mode. This deterministic hardware protocol is the mechanism that allowed early computer architectures to overcome catastrophic processing bottlenecks, offloading rote memory transfers to dedicated silicon.